Exploring general relativity with quantum computers, a new frontier in physics. Imagine a world where the principles of quantum mechanics and Einstein's theory of general relativity might not play nicely together. A groundbreaking study published in PRX Quantum suggests that a network of quantum computers, equipped with highly precise optical clocks, could reveal how these two fundamental theories of physics interact or clash right here on Earth. But here's where it gets controversial. Some experts believe that the standard quantum theory might need a serious overhaul to incorporate the effects of gravity, led by Jacob Covey, a physics professor at the University of Illinois Urbana-Champaign. The study proposes an experiment that could provide concrete evidence of how general relativity affects quantum systems. The researchers suggest that even a small difference in elevation, just about 1 kilometer, between 3 quantum computers, could be enough to detect the nonlinear effects of Earth's gravitational field on shared quantum states. And this is the part most people miss. The implications of this experiment could challenge the very foundations of quantum mechanics. There is a significant amount of theoretical work indicating that actual quantum mechanics entirely relies on optical clocks. The study proposes an experiment that can provide concrete evidence of how general relativity might enforce a chaotic sphere. The proposed experiment uses a network of quantum computers equipped with highly precise optical clocks and optical atomic clocks, the phenomenon of gravitational time dilation, a consequence of general relativity where clocks at different elevations tick at slightly different rates due to the curvature of spacetime. While this effect is most pronounced around extremely dense objects like black holes, it is still measurable on Earth using the ultra-precise optical atomic clocks. However, no experiment has yet directly observed how space-time curvature influences quantum mechanics itself. One of the key principles of quantum mechanics is the Born rule, which describes how probabilities in quantum systems are calculated. Theoretical work suggests that the curvature of spacetime could alter this rule, leading to new types of interference addings in quantum systems. To observe these changes, the experiment would use a 3-node quantum network, where each node is a quantum computer equipped with an optical atomic clock. These nodes would be placed at different elevations to create the necessary conditions for detecting Born rule violations. The Born rule predicts that in a system of 3 quantum sources, only pairwise interference is needed to describe the system, Covey elaborated. If gravity modifies the rule, we would see a new type of interference involving all 3 sources simultaneously. This requires a system with a high degree of nonlinearity, which is why we need the precision of optical atomic clocks and a significant elevation difference. The proposed experiment uses a specific type of quantum state called a W state, which is crucial for many quantum computing and communication protocols. By creating W states across the 3 quantum computers and observing the interference patterns, researchers can determine if the Born rule holds up under the influence of gravity. Covey believes that the technology to implement this experiment is within reach, thanks to advancements in distributed quantum computing. Illinois is already involved in building a quantum network through the QNext Department of Energy Quantum Center, which connects the University of Chicago and Argonne National Laboratory. Future plans include adding Fermilab and other locations in the Chicago area, potentially achieving the necessary elevation differences of nearly 1 kilometer. This research, which also involves contributions from Igor Pikovsky of Stockholm University and the Stevens Institute of Technology and Johannes Bodengard of Harvard University, could pave the way for a deeper understanding of the interplay between quantum mechanics and general relativity. The study, titled Prodding Curved Spacetime with a Distributed Atomic Processor Clock, is available online. What do you think? Could this experiment finally bridge the gap between quantum mechanics and general relativity? Or will it reveal that our current understanding of physics is fundamentally flawed? Share your thoughts in the comments below. Unifying quantum mechanics and general relativity. A theory of everything? Imagine a groundbreaking experiment that could finally bridge the gap between 2 of the most fundamental theories in physics. A network of entangled atomic clocks might hold the key to reconciling quantum mechanics and general relativity, potentially leading us to a theory of everything. One of the most significant hurdles in contemporary physics is merging the principles of quantum mechanics which governs the behavior of particles at the smallest scales, with those of general relativity, which describes the force of gravity and the fabric of spacetime. A novel experiment, detailed in a recent paper, proposes a method that could offer crucial insights into this long-standing puzzle. James Felton, a seasoned author with a knack for explaining complex scientific concepts, highlights the importance of this research. Felton, who has authored several books on history and science, emphasizes the need to explore the intersection of these two theories. The paper, co-authored by Igor Pikovsky from the Stevens Institute of Technology, Jacob Covey from the University of Illinois at Urbana-Champaign, and Johannes Beauregard from Harvard University, outlines a unique approach to testing the interplay between quantum mechanics and gravity. Quantum mechanics has revolutionized our understanding of the microscopic world, providing a framework for phenomena at atomic and subatomic levels. On the other hand, general relativity, introduced by Albert Einstein in 1915, has stood the test of time, accurately predicting the behavior of gravity on cosmic scales. However, the two theories are fundamentally incompatible, leading to numerous paradoxes and inconsistencies when applied together. But here's where it gets controversial. Quantum mechanics is built on the principles that point particles are nonsensical, and that the Heisenberg uncertainty principle prevents the precise measurement of certain properties simultaneously. These principles clash with the deterministic nature of general relativity, which describes gravity as the curvature of spacetime caused by mass and energy. As Valerio Faraoni and Andrea Giusti explain, any theory that combines these two must resolve these contradictions. Designing an experiment to test the interaction between quantum mechanics and gravity is a daunting task, largely due to gravity's weakness compared to the other fundamental forces. And this is the part most people miss. Most attempts to unify the theories have focused on high-energy scenarios, which are practically impossible to achieve in a laboratory setting. However, the new proposal suggests a more feasible approach using entangled atomic clocks. The experiment involves placing entangled atomic clocks about 1 kilometer apart. When these clocks are in a state of superposition, they experience different rates of time due to their varying positions in Earth's gravitational field. This setup could provide the first empirical evidence of how quantum mechanics and space-time curvature interact. Our protocol leverages two cutting-edge technologies, optical atomic clocks and quantum networks, to distribute quantum entanglement over large distances, the researchers explain. By creating a network of entangled clocks, the team aims to observe how the gravitational field affects the clock's timekeeping, potentially revealing the underlying principles that govern both quantum mechanics and general relativity. If successful, this experiment could be a monumental step toward developing a unified theory of physics. It could challenge our current understanding of both quantum mechanics and gravity, opening the door to new discoveries and theories. We assume that quantum theory holds everywhere, but we really don't know if this is true. Pikovsky adds, gravity might alter how quantum mechanics functions, and this experiment could test that hypothesis. The implications of this research are profound, and the results, if achieved, could reshape our understanding of the universe. Whether this experiment confirms existing theories or introduces new paradigms, it promises to be a pivotal moment in the history of physics. What do you think? Could this experiment finally bridge the gap between quantum mechanics and general relativity? Or will it lead us down a new, unexpected path? Quantum theory meets curved spacetime, a groundbreaking experiment proposal. What if the fabric of reality itself is a puzzle we haven't even begun to solve? Imagine trying to fit two of the most successful theories in physics, quantum mechanics and general relativity, into one coherent framework. It sounds like a riddle with no answer, and yet scientists are closer than ever to cracking it. A groundbreaking experiment proposed by Jacob Covey and his team at the University of Illinois Urbana-Champaign could finally bridge this gap. Their work focuses on testing quantum theory in the warped, gravity-bent spacetime of Earth, a realm where our understanding of physics teeters on the edge of collapse. But here's where it gets controversial. Some physicists argue that gravity might not even need to be quantized at all, challenging the very foundation of quantum gravity research. What if our obsession with unifying these theories is a red herring? And this is the part most people miss. The experiment's design hinges on a single, distributed quantum state spread across three atomic systems kilometers apart, each experiencing slightly different gravitational effects. By entangling these systems and measuring their shared quantum properties, the team hopes to uncover clues about whether quantum theory holds in curved spacetime and how spacetime itself might be quantized. But wait, what does that even mean? Let's break it down. Spacetime, the invisible stage where all cosmic events unfold, is typically treated as smooth and continuous in general relativity. Quantum theory, however, paints matter as discrete and probabilistic. Covey's team is asking, could spacetime also have a quantum structure, like tiny building blocks we haven't detected yet? If so, how would that affect the behavior of particles and fields? Their experiment uses optical atomic clocks, which measure time with extraordinary precision, to detect minute differences in proper time, the time experienced by objects in their own gravitational environment. By delocalizing a clock state across three systems at different elevations, the researchers create a quantum entangled state sensitive to spacetime curvature. The catch: the differences they're measuring are vanishingly small, requiring cutting-edge technology to isolate the signal from noise. This isn't just academic navel-gazing. The results could reshape our understanding of gravity's quantum nature and open doors to technologies like ultra-precise navigation or gravitational sensors. Yet, the challenges are immense. The entangled state required for the experiment is as fragile as a soap bubble, prone to collapse from the slightest disturbance. Similar hurdles plague other quantum gravity experiments, from detecting gravitational entanglement to spotting third-order quantum interference effects in gravitational fields. And here's a twist. The Born rule, a cornerstone of quantum theory that tells us how to calculate probabilities, hasn't been thoroughly tested in gravitational contexts. What if gravity violates this rule, exposing a flaw in quantum mechanics? That's the million-dollar question. Covey's proposal is part of a growing effort to move quantum gravity from theory to testable science, but it's not without skeptics. Some argue that the entire pursuit is misguided, that gravity might emerge from quantum effects rather than being quantized itself. Where do you stand on this? Is the quest for quantum gravity a noble endeavor, or are we chasing shadows? Share your thoughts, because the answers could redefine physics as we know it.